Do I need to turn it on? Yeah, it's okay. Hello, everybody. So I'm going to be talking about turbo-geth, which is a derivative of the Go Ethereum, which you're probably all familiar with. And it's aimed at improving performance and reducing the cost of running full nodes and archive nodes. So maybe not like a personal wallet, but more of the infrastructure backbone. And I need to mention, and I'm really grateful to Ethereum Foundation to provide a grant for this work. So it started off late last year when I was looking at the why I was trying to understand why the Ethereum client slowed down during the CryptoKitties period, and I decided to just use the profiling option of the Geth, which makes it very easy. If you're ever curious about what's going inside it, you can do the same thing, and then use the Go tool chain in the bottom of here to just visualize it, like where does the time go. And here, in this example, you see that I was syncing 5 days worth of blocks, and it took me about 3 hours. And I must say that with the current version of turbo-geth, it takes 3.5 hours, so the work is far from done. But you will see that there's other facets to it. So what I kind of got at that point of time, this kind of profile, but the most important thing I learned from this was that here in this corner, you've got something called the secure tree over here, and it was trying to read this thing from the secure tree. And right on that side, you can see that this ends up going into the level DB database. It's reading and writing in it. And so this is where I started to go down this rabbit hole and trying to find out what is this, what's that, and so on. So we'll have to talk about Merkle trees for a bit more, because the secure tree which you saw there is actually a Patricia tree with randomized keys, and I'm going to derive it very quickly through some couple of slides. So you all know about, a lot of you might know about Merkle trees, which is basically improvement over the hash of a concatenation of some strings in a way that it allows you to make a compact proof of membership, and not just, in this case, the proof of membership is all the list elements. Oh, sorry. Does it not roll back? Okay, so yeah, sorry. So the proof of non-membership is a bit harder, because in a regular Merkle tree, it will again consist of all the elements, but if you sort the nodes ahead of time, you can actually do something on which I show over there, which allows you to see that something is not present. But then what you really want to do when you keep modifying your data, you also want to not rebuild the tree every time you add or delete the entries. So you want to preserve the structure as much as possible. So in this example, when we remove the J, we essentially replace a few items. So the pink items with the green items. You can see the dotted line connects the gray elements, which we're still reusing, but I had to separate them for the illustration. But basically all the gray items, gray nodes are reused. And this is what you want to be doing, because you don't want to be recreating the tree all the time. Another way, but how we're going to do this? So in Ethereum, the approach has been taken, it's called radix tree, where the position of the element inside the tree is dictated by its key. So you can see that, like a duck, for example, it starts with a D and then goes over there. And so by definition, this kind of tree becomes sorted, but this is not the only way to achieve this property, meaning that it's not the only way to preserve the structure during the modification. You can also use the tree balancing algorithms, like the ones which is used in red-black trees or in AVL trees. And Tendermint, for example, uses the Merkleized AVL plus trees to achieve this thing. And so it's not the only way, but that's how Ethereum does it. And one thing to notice that the radix of this tree is 26, because essentially every key could be treated as the word in a 26-letter alphabet, or like in a number of the 26, in a number system with a radix of 26. So here what we see is this is how our radix tree looks like. And in this illustration, the radix is 4. But Ethereum uses radix 16, so it's got 16 children of each of the parent. And you can see, like, if you try to just randomly putting stuff in this radix tree, you will notice very quickly that there's this big segments of the nodes which have only one occupied digits. I call them noodles sometimes. It looks like noodles. And this presents an efficiency in terms of space and also in terms of processing. So there must be some other thing we need to do to okay, so this is where Patricia comes from. So it's acronym, and essentially the trick is to replace these segments of one-digit nodes with something called leaves and extensions, depending on whether they are on the bottom of the tree or they're in the middle. And if you look at the Go Ethereum client node, you will see that these are called short nodes and these are called full nodes. So now this is what the Patricia tree does. It takes the radix tree and then replaces this long strings into the kind of compressed versions where you just specify the part of the key and then the value. So you can see on that side that we have a 3-leaf node and 1 extension node because it's in the middle and then it branches off after that. And as I said already, the Ethereum has radix 16, and also in Ethereum every key gets hashed with this hash function, and result is always 32 bytes, and that means that with the radix 16 the maximum depth of this tree is 64. You can make a computation later on. Okay, so this is very quickly, I'm not going to talk a lot about this, but in order to understand what is going to be on the next slide, just very quickly, what is RLP? Is essentially a serialization format in Ethereum, and it allows you to encode and decode single bytes, byte arrays, and sequence of RLPs, which is why it's called recursive. And this is where to show you how the state is currently stored in Geth, and I probably would be fair to say this is how it works in Parity and Harmony and other clients. So essentially, if you have a Patricia tree like this, so the database remembers the RLP encoding of each node in this hash tree, and it remembers under the key, which is the hash of this RLP. So you can always look up, if you know the hash, you can look up in a database and you get the RLP. And so now imagine that because if the tree gets really large and we cannot keep it in memory, sometimes we have to offload it to disk. And so let's say here we offloaded these 2 diamond nodes and we only keep this one, but we remember the hashes of the diamond nodes, and imagine that we need them again at a later time. So let's say we need the pink node over there, and so what we do is simply take the hash out from here, look it up, and then we get the RLP and recover the pink node. And now imagine that we don't have that either, we just have a root and this underneath. So now we have to do 2 lookups. First we use this hash to look up that node, you see, and then we, after we've done this, we know the hash of the pink diamond and we do it again. And as you can see in the process of this expansion, there is a data dependency between the steps. So we don't know the hash of the pink diamond until we looked up this one. So that means that it's inherently sequential process. You cannot parallelize it, you just have to do it one by one. And that leads to another observation, that the depth of the tree really matters, and the performance of the lookup of this expansion degrades with the depth of the tree. So now let's have a look. So this is okay. So I've done a snapshot of this Patricia tree of main chain Ethereum at around the block 5 million, just to show you. So on here you've got the different levels of the tree. Up to the level 12, there's nothing after the level 13, and there's not much after the level 6. And the reason for that is, you might know that all the keys get hashed with this secure hash function, which essentially means that they get randomized. So it's another way of balancing the tree. So they balance such a way that there's nothing after this point. And in the columns you can see different occupancy levels of each node, and it's expected to see that most of the up to the level 5 is pretty saturated. So we got complete occupancy on the first 5 levels, and after that we got a little bit of a little bit less nodes. And you can see the first column shows that this is where the leaf nodes live. This is just one, because they get compressed by the Patricia tree. So this is basically, the most of the leaf nodes, well, that time was were living on a level 7. So remember the depth is really important. So this is how turbo-geth does it. So instead of doing actually I crossed out the Patricia here because in turbo-geth we depart from the idea of storing Patricia tree in a database. Instead we simply store the key value pairs over there, and it's pretty trivial to imagine apart from that suffix in the end, which is block nr. And why we didn't block nr is essentially if you have let's say if this is the account and this is the account with a very long history, it has received like 1,000 transaction and sent another 1,000 transaction, then it will have multiple records but with different block nr, and that allows us to quickly find the specific entry as of specific timestamp. So I call this block nr timestamps because it could be generalized. And so, but how do we do the lookups? Let's say that this part of the trees is currently offloaded onto disk and it's not present in memory. So what we do, we just have this bit, and so what we start to do is that we do this range query, which I'm going to be talking about later, where we say I want everything which starts with 1 and everything after that doesn't matter, and actually I also want the block number more than something. And using my specialized range queries, we can efficiently produce the results. In this case it's going to be 2 entries, and then we essentially apply the whole hashing again through the rebuilding this part of the tree, and we just stick it over there, right? I will talk about this range query a bit later, but essentially you can see there's no Patricia tree in the database at all, and that has some interesting consequences. Which way? Up? Okay. So now let's see, this is about the geth, not turbo-geth. And very quickly recap how does the state interact with the Ethereum state machine. So the computation is running in a virtual state machine, and for each block, during each block it maintains this transient state and a journal. So the transient state is where we record all the modifications to account, storage and other stuff. The journal is required to very quickly revert the changes when, for example, revert opcode is used or there's run out of gas and stuff like this. So after each block or after each transaction before Byzantium, the state gets miracleized and sent off into well, committed into this state forest. I will tell you about it, why is it forest, a bit later. And then once in a while it gets committed into a database in the structure that I showed you before with this SHA-3 ROP thing. And when you do the data queries like RPC, for example, you're asking for like state of the account, a particular timestamp, or you want all accounts modified within this range of blocks, you're essentially going through the state forest. And then state forest, when it doesn't have that data in memory, queries the database. So let's see how it looks in turbo-geth. Because we don't really, so because we essentially, the database doesn't know anything about the tree, they can be almost completely decoupled. And that has some interesting properties. So here we've got, again, virtual machine, transient state, everything is the same. But when we commit the state, it actually goes to both things using the common interface. So in the code it looks like the same thing, but we just substitute tree. Do you want to go into tree or do you want to go into the database? And the nice thing about it is that when you do RPC, you don't even need to know about the tree. You just go straight into the database. And because, as you saw, the database layout is very straightforward, my hope is, unfortunately I didn't benchmark it yet, that this will allow you to do much more performant and cheaper queries to the state. And okay, so now a bit more differences. So early on in the project, I decided to experiment with the bold DB, to replace the level DB with it, and I'll very quickly show you the difference. So the level DB and also the rocks DB, which is a bit of a derivative, they use this write-ahead log with a background compaction. which means that the random writes are pretty quick because you just need to put it into a write-ahead log and then something else happens in the background. But you pay the cost of this by what they call the write amplification, which means that every bit of data has to be rewritten multiple times, that it moves up the levels. And there's also read amplification, which means that you have to check multiple levels to see which one is the right one. In a BoldDB, it follows the traditional B plus tree index, which is a very popular structure in databases. And the downside of it is that when you insert or delete or read the data, you have to find exactly where it is or where it has to be inserted. But what I'm doing is that if I'm batching up all these reads and writes to the database, and I developed this guided traversal approach where you so when you traverse the B plus tree, when you deliver the piece of data, you actually do it via callback. And this callback is returning you the value, which means that, okay, so after this, you need to jump to another value, which may be over here. So let's say that I've delivered this piece of data, but then it said, I want this piece of data now. So it goes up the tree to the page where there contains both the current key and the target key, and then it descends down the tree. And if you batch up a lot of operations and use this guided traversal, meaning that you only need to traverse the tree once to do all the work. So, and that took a lot of time, but it actually works now. Another thing is that because my batches are so large, they become bottleneck on their own when they're in memory. So I had to I just got some library with a red-black tree, but even there I have to modify to be compatible with these guided traversals. So now, talking about the forest. The reason I called it the forest in Geth is because the Geth actually remembers 128 by default, past state root hashes. In order to be able to quickly go back, if there's a reorg, it just quickly goes back and remembers, okay, I need to revert the last 10 blocks, it goes back 10, and then it rebuilds the tree after that. In a turbo-geth, I only keep one version of the tree at a time, and the reason for that is another thing is that I want the tree nodes are being mutable, not immutable but mutable, so that I don't have a so-called memory churn, because if you keep allocating, deallocating, there's a lot of it actually eats a lot of performance, as we will see later. So, but it creates challenges for reorg. But luckily, using the same guide traversals, I can basically efficiently replay all the blocks back from the current tree and reconstruct what the tree used to be before that, and then reapply the side of the fork. So now let's look at some data. So this is basically the sink, and here I compared the performance. This is the turbo-geth, the latest code. It doesn't work completely because there's a consensus failure to block about 5 million, but that's work in progress. So the blue area shows the SSD, solid state drive, a computer with 26 gigabytes of memory, but not all of them are used, and the purple ones are HDD. So one of the goals of turbo-geth is to equalize their performance so that you can use the cheaper hardware to run your nodes. And as you can see, that everything was fine until this spam attack of 2016, where the HDD started to fall behind. And I will be looking at this later on. But you see, later on, they're actually okay now. So, and this is the memory. So the green line is that it's a number of nodes resident, of the tree nodes resident in memory. And I have this option now that to limit, at the moment it's like 4 million. And the idea behind this option is to calibrate the memory usage using this option, but you can see it's not working very well yet. So the yellow bit is that how much memory it actually uses. And this is the disk usage. So one surprising thing that happened is that at around block 5 million, you get block receipts taking a huge part of the disk space, and actually it gets worse. But the good thing about it is that compared to Geth in archive mode, which takes 600 gigabytes, the turbo-geth for the same sync takes 200 gigabytes, so it's 3 times less. So that's one of my hopes. And okay, so now if I did the profile right now, which I did, there's you can see lots of issues here. So this is the garbage collection, the memory churn that I noted when I mentioned. This is essentially the database operation with this guided traversal. But actually, I'm quite happy it's only 5%. So this it's not very well to see, but it's actually ECDSA recovery. It's about 10%. It's when you try to recover from address, from the signature. And the last thing is that here you got the hashing inside the Merkle tree. And actually, most of the time is spent on ROP encoding, not on the hashing itself. And so here's my own bit, is that tree pruning, which I could improve as well pretty easily. And I think that's the end. Thank you very much.
Good job.